we had a carry before that. So let's just do this 1, and then you write down the 1. 1 plus 1 is a 0 with a carry. So now that carry comes in, we got a carry plus 1 plus 1 plus 1. That's actually with 2 carries, because the answer turned out to be 4. And 4 is made up of 2 and a 2. And remember, 2 would have been 0 with a carry. The other 2 would have been 0 with a carry. So that's why we ended up with 2 carries. So now in the 4th column, we got 2 carries coming in. So it's 2, 3, 4, 5, 6. That's actually, since it's an even number, that's going to be 0 with 3 carries. So now we're going to have 3 carries coming over here. 3, 4, 5, 6. That's 0 with 3 carries. And now we got 3, 4, 5. That's an odd number. So that's 1 with 2 carries. 2 carries plus the 1 is 3. That's an odd number. That's 1 with 1 carry. And then that 1 carry ends up right here. So that's how we got that answer. So you're going to get a series of 1s that are getting larger and larger. So you have to watch out whether it turns out to be an odd or an even sum to know whether or not you put down a 1 and how many carries you have. So make sure you try these out and make sense out of it. Okay, and finally in this section is division. Division uses the same procedure that we used in long division that we learned back in grade school. So, for example, when you take 3 and you divide it into 9, so it would be 9 divided by 3, right? We get 3. You multiply the 3 times the 3, you write down the 9, subtract, see if you have any remainder. In this case, 35 divided by 5, you divide 5 into that, it turns out to be 7. You write down 35, subtract, you get 0. Now, in binary, you would write this out. First of all, you write down the 3 as 1, 1, and then you write down the 9 as a 1, 0, 0, 1. And you take the 1, 1, you see where it fits. It won't go into the 1, 0, but it would go into the 1, 0, 0 one time. And then you take 1 times the 1, 1, and you write it down carefully in the right spot, and you subtract. 1, 0, 0 is really a 4. So you have 4 minus the 3 is a 1. Carry down the 1 that's left, and now you take 11 into 11, or I should say 1, 1 into 1, 1. You get a 1 with no remainder. That's the final answer, 1, 1. Check, worked out. How about 35 divided by 5 should be 7. Again, the 1, 0, 1, you see where that'll fit. It won't fit into 1, 0. It won't fit into 1, 0, 0, but it will fit into 1, 0, 0, 0, which, as we know, is the number 8. So you're really taking 5, dividing it into 8. Turns out to be 1. You multiply the 1 times the 101. Make sure you line things up properly. Subtract. You end up with 1, 1. Bring down a 1, and so on and so forth. So what you need to do is go through this example 7-4 carefully on your own and see if you can do this longhand binary division. And then later on the page, here's the other 2 examples, part C and part D. This will be 135 divided by 15 and 221 divided by 17. So that concludes section 7-1. Next, in 7-2, we're going to look at 2's complement representation and 2's complement math, which is another method used for addition and subtraction. So that's it for this section. Hi, this is Professor Kleitz. In the next 2 sections, I'm going to talk about 2's complement representation and the arithmetic. The most widely used method for representing binary numbers and performing arithmetic in computer systems is by using the 2's complement method. With this method, both positive and negative numbers can be represented using the same format, and binary subtraction is greatly simplified. When you look at figure 7-4, I'm showing an 8-bit number and a 16-bit number. The key element is the leading or the most significant bit is always used as a sign bit. If it's a 1, the remaining bits are used to represent a negative number. If it's a 0, the remaining bits are used to represent a positive number. Same with the 16-bitter. So because the first bit is used for a sign, the range for positive numbers is going to be all zeros up through 0, 1, 1, 1, 1, 1, 1, which is actually the number 127. For negative numbers, it'll end up being 1, 1, 1, 1 to 1, 0, 0, 0, 0, 0, which is actually a -1 to a -128. And in a moment, we'll see how we got those numbers. In general, the maximum positive number will be equal to 2 to the n -1. The maximum negative number will be negative 2 to the n -1, raised to the 2 raised to the n -1, where n is going to be the number of bits in the number. So this will either be the 8 or the 16. Okay, so how do you make this conversion? First of all, if the decimal number that you're trying to represent is a positive number, the 2's complement is just the basic true binary equivalent. So like if you said, what's a 2's complement of a plus 18? You just write it out as you would as we learned back in chapter 1. This is a 16-bit and a 2-bit, right? If the decimal number is negative, the 2's complement is found by, first of all, you complement each bit in the true binary equivalent. So you would have taken this 18, flip every bit. This is called the 1's complement. And then you add 1 to the 2's complement number to get the magnitude bits. The sign bit will always end up being a 1. So if you look at example 7-5, let's say we get the number 35, the positive 35. First of all, the regular binary for that would be the 32-bit, and then the 2-bit, and the 1-bit adds up to 35. So the 2's complement is just that number as is. So in the next example, we're going to take the same number but make it negative, so negative 35. So again, the true binary is 0010, 0011, as we saw before. Flip each bit, it's called the 1's complement. So now we have 1101, 1100, add 1, and when you add 1, here is our answer. That is the 2's complement for a negative 35. So table 7-3 gives a list of the 2's complement numbers from a +7 down through -8. And you can see what's going on when you look at this. Here's a 7. We've seen that before, right? And they'll start going down by 1 each case. So there would be 6, a 5, 4, 3, 2, 1, and 0. If you subtract one more, you think about it, that would end up being 1, 1, 1, 1, right? So it just kind of rolls under. So that's a -1, -2, -3, -4, and so on. And if you perform those rules that we just listed before to any of these negative numbers, you'd see that they all worked out this way. So now, of course, we need to be able to go the other way. When you have a 2's complement, you want to go back to decimal. So to do that, follow these steps. If the 2's complement number is positive, you can tell by the sign there, right? Just do a regular binary to decimal conversion like we did back in chapter 1. If the 2's complement number is negative, having a sign bit of 1, the decimal number will be negative, and the decimal number is found by, first of all, you complement the entire 2 bits number bit by bit, add 1 to arrive at the true binary equivalent, doing a regular binary to decimal conversion to get the decimal arithmetic value. So let's look at a few examples of doing this conversion. So in example 7-7, let's say you have this string of bits. Obviously it's a negative because you got the sign bit is turned on. So the 2's complement number is listed out here. You complement bit by bit, add 1, and when you add 1, you get this string. So here is the true binary number, and then you just do a regular conversion back to decimal, and that's a 32-bit, a 2-bit, and a 1-bit. That's number 35. Don't forget to put the minus sign in front of it because we had a sign bit. How about the -98? So you list it out in true binary, flip every bit, add 1. There's a true 2's complement number. Actually, I was doing decimal and 2's complement. And then the next one, 7-9, actually, is the one I was thinking. This one, we're going to convert 2's complement to decimal. So again, we've got a sign bit, so the decimal result will be negative. So you write down the regular 2's complement, straight from what we had in the problem. Complement bit by bit, add 1. And here is the true binary number, which is the 64-bit, the 8, the 4, and the 2, which adds up to 78. Don't forget the minus sign. So now in section 7.3, we'll use 2's complement for doing our arithmetic operations. All 4 of the basic arithmetic functions involving positive and negative numbers can be dealt with very simply using 2's complement arithmetic. Subtraction is done by adding the 2's complement numbers. Thus, the same circuitry can be used for addition and subtraction. So there's no need to always subtract the smaller number from the larger number. We must be careful, however, not to exceed the maximum range of the 2's complement number. That would be +127 to -128 for 8-bit systems.